Morning, everyone. This is a new thing. For a lot of this class, I prepared all the lectures in advance. And for the reverberation time unit, I did prepare an example and things to help you get going. But I figured I'd talk through the slides very briefly. And I hope this doesn't take long. And I thought I had this done, so I'm sorry for not having it up sooner. But I will just do it now and notify the entire class that it's ready. So here we go. So the goal of the week is going to be to quantify reverb somehow. So administratively, I've already announced that the quiz is online. You can see that. The goal is to quantify reverb. And we're on chapter 10 of the course notes. So that's where we are. If I were to ask, what happens to sound waves as it travels around, or as they travel around a room? Sometimes people give me very complex wave phenomena. They want to talk about like diffraction or something like that. That's all valid, but for the purposes of understanding reverb, we only really need a couple of things. When an incident sound wave comes in, some of it bounces off, some of the energy gets absorbed, some of it even could go through. And what we want to do is connect the properties of a room and the properties of a wall to what the sound environment's going to be like. Okay, so some wall facts is that big, smooth, stiff walls reflect most of the energy they receive, and softer materials can absorb more of the energy. So picture like egg crate foam or carpet if you want something cheaper, or maybe fiberglass, things like that. They can absorb more of the sound and energy. So naturally, I mean, the intuition should go, the more reflective the walls are, the more reverberation you're going to get. If you think of reverberation as an effect you get because sound is bouncing around the room. All right. Now, heavy walls aren't always feasible. I mean, to prevent transmission, you could install some kind of insulation that may be good for heat or for sound energy. We get the phenomenon of reverb because sound can take a lot of different paths to you. I'm not going to spend a lot of time talking about the precedence effect. I mean, you'll learn in audio what kind of cues our ears use to localize things. If something is off to one side, my brain can tell even with my eyes closed because the sound will get to one ear first. And so there's a time difference and a level difference between what my two ears receive. The precedence effect will help my head cue. You know, if there's a lot of reflections in a room, my head will cue to the one that comes first, and that's how I locate. But I mean, the fact is, right? These sound waves can bounce all the way around. If you go inside, like like a boomy room or a bank vault or something like that, the echoes can persist for a very long time. You get echoes from all the walls in the room and the floor and the ceiling. You don't hear distinct echoes unless the sounds are separated. And that separation, it depends on what it is. So like if it's speech or music, you won't hear like separate echoes as readily as you will for a click. Like if a click comes out and there's a time difference between the direct sound and a reflection that's big enough, you'll notice a difference, and the difference and the time difference you need to notice it as separate is very small for a click versus speech or music. Right. So basically, the more possible paths sound can take, the more reverberation you will hear. And one way we quantify that is, right, if sound energy gets absorbed, it's not around to create these reverberant echoes or these reverberant reflections so much. All right. So how we quantify reverb? Now, I've already linked to you a podcast called 99% Invisible on the Canvas page. And this is the first place I'd heard the name said. I've read it written in print, but I believe it's Sabine. It's how they say the name, and the unit of absorption area is named after this, although that's called a Sabin, I believe. And Sabine's equation is the way that we quantify reverb. If you listen to the podcast I linked to on Canvas, again, this is right. 99% invisible. You can search for architectural acoustics. That particular episode, and I linked to it in Canvas, but he was tasked with solving a problem. So Harvard had built a speech hall that had bad acoustics in it, and they gave him the problem, right? Can you figure out what's going on here? And so we very meticulously worked on experiments in different concert halls and different rooms to figure out the reverberant qualities. So what you would do is you turn on a loud organ pipe, you let it kind of saturate and you fill the room, and then you shut it off and you time how long it takes to decay away. So this is how we quantify reverb, by what time that is. Okay. There's a specific meaning for it. Reverberation time is a number of seconds. And here's the way you think about it, right? You turn on your sound, you let it fill the room, and this fraction of maximum intensity here, it tops out at 1. So you saturate the room with some maximum intensity. If you leave an organ pipe on, the sound isn't going to keep getting louder and louder forever. There's going to be some level where it tops out. Okay, and then you shut it off, and because some of that energy will be reflected, some of it persists, some of it gets absorbed in various places, and so that intensity will decay away. So what the reverberation time is the time it takes from that moment you shut it off to when the intensity is 10 to the minus 6th times as much. That's 1/1,000,000th. So that's how we quantify it, right? You take the maximum intensity and you figure it out. How long does it take for it to die off by a factor of 1,000,000? Okay. Now there's two ways of writing this. I can think of normal intensity as 1 and the died off intensity as 10 to the minus 6 times that. Okay, we can define RT that way. RT is reverberation time. Or we can put this on a decibel scale. Okay, so we can call like the fully saturated level just 0. And every factor of 10 less intensity is 10 fewer dB. So a factor of 1,000,000 down corresponds to a 60 decibel drop, something we learned about in a previous class. So we could say the reverb time is the time between when a sound source is, right? First you turn it on, and then you start the timer when you turn off that sound, and then you stop it when it's died off by 60 decibels. That's a factor of 1,000,000 in intensity. So these two graphs show the same thing. They may look a little bit different. You might notice this one on the right is a straight line down, but that's something that happens when you convert from an absolute scale to a logarithmic scale. A logarithmic scale takes exponential decay and it turns it into a straight line graphically. Okay. So that's what the RT is. You will always see it as a number of seconds, right? And a room that's very boomy and reverberant will have a very long reverberation time. Something like a vocal ISO booth will have a short reverb time. And that's what this slide's about. So good orchestral halls have reverb times of 1 to 2 seconds, but it's slightly complicated for reasons we'll see in a little bit. I linked to one claim which says, like the Symphony Hall, I want to say in Boston has like an ideal 1.9 second reverberation time, so something like this. So like big concert halls, you're going to want it on the high end of the 1 to 2 second region, but a recording studio or an ISO booth will have a reverb time less than a second, maybe even less than half a second. It's pretty reasonable. So that means it takes less than half a second if you shut a sound off for it to die away. And in a reverb, in an isolation booth or a recording studio, you want that. You want it to be as dry as possible. So if you want to add reverb and effects, you can do it in post and you can control it. Now, some recordings, I think Led Zeppelin and Queen were both famous for examples of this. Like you want reverb on purpose, and for live performances, playing it in a concert hall or a church or something like that is what you want. Like the natural acoustics of the room give you a reverb that maybe your sound wants, but that depends on whether you're performing or recording, or if you want that sound in there or not. Okay, so some resources refer to RT30 or RT20, so how much time it takes to drop 30 or 20 decibels, because those are easier to measure. But Sabine's formula talks about RT60, and that's what we're going to calculate here. So How do you calculate it? You have to know how different materials absorb and transmit sound. Okay. And so what we assign is a number called the absorption coefficient. So an absorption coefficient says how absorbent is a material. The definition of it is absorption coefficient is the energy absorbed by a material divided by the total energy that it gets. So this symbol, and this should read alpha here, the Greek symbol alpha. I can convert it by going to the right symbol font. That's how I type all my Greek. Okay. So alpha has no units, and it depends on what the material is and what frequency the sound is. So back a slide or two ago when I said a symphony hall has a reverb time of 1.9 seconds, that's not entirely precise because normally you'd have to specify what frequency you're talking about. Every frequency is absorbed a little bit differently by materials. So the range of alphas is between 0 and 1. If a material absorbs everything it gets, then the energy absorbed divided by the total energy is 1, because it's the same number. If a material is perfectly reflective, then it absorbs nothing, and so the alpha will be 0. And alpha has no units at all. It's just a number between 0 is the smallest, 1's the biggest. All right. So that's the range of alphas that we can have. And normally I would supply these to you in a question. So these two slides show that off. For a given frequency, here are some absorption coefficients. You can notice that occupied seats and acoustical board is pretty high. Occupied seats, the alpha is high because if there's people in it, we're basically bags of water, and that absorbs a lot of acoustic energy. Fiberglass and acoustical board are also more absorbing surfaces, absorbing materials than others. Okay, but something like brick and concrete, they're going to reflect almost everything they get. If you make a wall or a floor out of that, and so the absorption coefficient is less. Okay, for a given material, depending on the frequency, you'll get a different number. So usually when I give a problem, I'll specify what the materials are, what the frequency is, and if necessary, I'll give you the absorption coefficients. You won't ever have to memorize those. Okay, but we can see, like, one example: carpet on concrete on the right. At very low frequencies, the absorption coefficient is low. It's mostly a reflective thing. But at higher frequencies, you're absorbing over half the incoming sound. So that's why different frequencies will have different reverberation times for a given room. Okay, and how do we put this all together? Well, there are two formulas. Okay, right. Both of the formula, and it's kind of sloppily drawn here. You see, like Microsoft, the PowerPoint isn't letting me edit this quickly because it's an import from another version. It's kind of messed up. But what the equations look like is you have a number in the front. It's either 0.05 or 0.016, and then multiplied by volume divided by an area. Okay. Now, for ultimate detail on this sort of thing, go to my video that's already posted, where I go through how to use this formula. Now, V is volume. That's something easy. We're going to do only rectangular rooms, so volume is length times width times height. Now, the trickiest thing in this formula is what this A is. And A is called the absorption area. Now, you might think you just take the area of all the walls, but not quite so simple as that. Right. To get the absorption area right, you have to factor in and use the absorption coefficients. So I will show you a slide of how that goes. But you have to use the absorption coefficients. In my video and my sample worksheets, which I've posted, show how to do this in detail. I'll explain a little bit also, like the constant that you use to this 0.05 or this 0.16 that you use in front depends on whether your measurements are in feet or in meters. It matters, right? Now, for a given room, the reverb time is what it is. It doesn't really care whether you use a foot ruler or a meter ruler. It's just that the volume over area ratio, even if you're not changing the room, the volume over area ratio does change depending on whether you use feet or meters. So that's why we need the different constants in front. Now, what the absorption area is, it's equal to the area of the surface multiplied by the absorption coefficient. So basically what that says is if your wall has a fiberglass or egg foam or something on it, you're going to multiply the area by some high number, and almost all of that area will count as absorbing. But if it's like low frequency on concrete or something, the absorption coefficient is very low. So I mean, you could have a very big floor or a big surface, but if it's made of something that isn't absorbing, it's not going to count that much for absorption area. And here's a summary of how to do it. Again, my other videos show in detail how to do this a little bit better. But the way to find the area of a wall is length times width, and the absorption area is the absorption coefficient of wall 1 times the area of wall 1 plus the absorption coefficient of wall 2 times the area of wall 2 plus da 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 da. And usually a room has 6 surfaces: up, down, left, right, front, back. Okay, so the way I do it in my example is I write out a table of all 6 surfaces. You find out what the area of each one is, and then you multiply that one at a time by the absorption coefficient. That's how you account for the material that each surface is made of. I also have a slide. I don't think I need to talk through it, but I'm justifying here, and my notes do it too, right? Yeah, why is there a 0.05 in one formula and a 0.16 in the other? And I just do 2 examples of why V over A is a different number depending on whether you measure a box in yards or in feet. And so V over A it's a factor of 3 difference when you're comparing yards and feet. It's a little bit more than a factor of 3 difference if you're comparing meters and feet. So that's why you have a 0.05 in one formula and a 0.16 in the other. You can see on Canvas 2 examples where I do 1 in feet and 1 in meters. You can kind of see the difference. Okay. So the example that I'm going to do on Canvas is I'll give you the dimensions of the room, and I'll draw it out, and you'll see there how I do it. I make up some materials for the walls, and you can find the reverberation time. Some recommended times, which I've stolen from a source online here. You can see for concert halls and church music, you want your reverb time to be over 1.5, maybe slightly over 2 seconds. Speech auditoria, you want the reverb time to be less. If it's too high, then it'll be boomy and you won't be able to hear the words that are being said. The opera theaters kind of split the difference because opera is lyrical. So you want the reverberant quality of the music to be good and the resonance of the singer to be good, but you also want to be able to hear the enunciation because right, opera singers work hard on getting their other languages correct. All right, so those are typical reverberation times. Right, again, I would take points off this graph a little bit because it's not indicating that this is reverb time in seconds. You should know that it's in seconds. Okay, and again, go to my other page or my other video where I do an example of how to calculate this for a room. Okay, so we're quantifying reverb here. You're going to get a large number of seconds, like 1 or 2 or slightly more, if your room is very boomy. And if it would act better as an isolation booth, you're going to get a small reverb time. Right? That's all. Again, sorry that this is late, but I'll get this up right away. Cheers.